Okay. So we're going to talk a little bit about lambda expressions and what lambda is. I think so. I'm using here the Visual Studio Code environment, and this is the dev container or the Docker um, image of Haskell that Finley McElwain made for the class. So I guess maybe I'll first open a new file and I'm going to save that as, let's see, I don't want it to be that. I want, let's say, lambda.md, which is a markdown file. And so now there should be some markdown tools here. But in any case, what is a lambda calculus? So lambda calculus was developed by Lonzo Church around 1930, I think 36, but I'm not sure. It was a pretty exciting time, actually, for logic and the beginning of the study of computer science, and lots of interesting things were happening right about that same time. But anyway, what Church was doing was he was at Princeton University, and he was trying to develop a calculi of functions, a way of talking about functions. Like, if you have a function f, x, y, and it's, I don't know, it's x and some, operator y. What's the difference between that and f, x, y equals y operator x? Like, those are different functions, but they're doing, depends on what the operator is. And so he wanted to be able to think about these kinds of things. And so he defined this language, and we'll call them Lambda. The language is really, really simple. There's only three things in it. You can write down a variable. X is in, a variable. I wonder if this works. X is in some set B var, where you can just think var is some unbounded set of lambda variables, x, y, z, w, x prime, y prime, comma, z prime, comma, w prime, dot, dot, dot. Whoops. So you got an unbounded. You have to always be able to get another one. You can have something in the form, if m is a lambda term, you can apply lambda term m to n. So I'm just going to say down here that m and n are in lambda, which means, and I'll say previously constructed. Now, what that means is that M and M have already been formed, syntactically well formed. I'm defining the syntax here. And if they have been, I can write them next to each other, meaning like this, meaning apply M to N. And the final thing is lambda x dot M. And so X again is a variable and M is a body. And so the idea here is that, lambda x, so I guess I should say that, maybe I'll try and insert it up here over this. So this thing here, this is a var. This thing here, that's a variable. This isn't called an application. Of M to N, and spread this out a little bit more. then this thing here is called an abstraction. Because you're abstracting x out of m and making it a parameter. Okay, so maybe these vertical bars here don't make any sense. So one thing is that I'm using here something called, which is commonly called a BNF style of describing the language. I'll say the grammar of the Lambda calculus. So the point is what are the things in here? Now in Haskell, we have exactly, I guess I should say, in Haskell, we have exactly the same things, except that instead of writing lambda x dot m, we write \x arrow m. And so this really looks a lot like the original as a subset. I guess maybe the way to think of it is a subset of the Haskell language is lambda calculus, or lambda calculus is some subset of Haskell. You can write all the things you can write in the lambda calculus here in Haskell. Well, not entirely, because Haskell won't, you can write them, but Haskell won't let you evaluate them if they're not well typed. And some of the things that you can write in this language that Church had, which is the untyped lambda calculus, you cannot write down in Haskell. So what is the idea here? The idea here is that this is a way of writing down a function of one variable, x, and x might appear in m, in the body of m. And so what about this thing that we had before? We had kxy is equal to x. Now, this is not a term in the lambda calculus. We don't have any equal sign. It doesn't mean anything in the lambda calculus. But what if I wanted to define a lambda calculus function that's the same as k? I would say, okay, it takes an x, and then it takes a y, and it returns an x. The simpler one, ix equals x. Well, this is not technically a lambda calculus term, but this one is lambda x arrow x. And so the idea is that any place, this is just binding a name to a function that takes an x and returns the x. kxy in Haskell, perfectly valid Haskell, is binding the name k to a function of two arguments, x and y, that returns x. And we can do the s x, y, z is equal to xz applied to y applied to z. Again, this one can just be, so, I could say here in Haskell, I could write I is equal to that. So this term over here is a pure lambda term. This is a pure lambda term. Well, maybe I won't bother with doing that. I'll just leave the equivalent pure lambda term down below. And then here, we've got lambda x, lambda y, lambda z. I won't put a space in there. And then I've got xz applied to y applied to z. So this thing here is a lambda term that is the same function as s. This here is a lambda term that is the same function as k. Oops. A lambda term. Now, what do I mean by is the same function as? Well, I mean, those are equal. K is equal to lambda x arrow lambda y arrow x. So we can try some of this down here. Haskell, I guess I got to say, where am I? I'm in the right spot to be able to start up, I hope, the interpreter. There's the interpreter. And so I can just try something like, I can say I equals, well, let's just start out like this. Lambda x arrow x. If I ask Haskell, what's the type of that? It says, oh, that's a p arrow p. Okay, that's good. That's what we want the identity function to be. So what if I apply lambda x arrow x to 5? I get back 5. What if I apply to x, y, z, z, y? I get back x, y, z, z, y. What if I apply it to lambda x arrow x? Well, this is actually not a problem. It's just telling me that Haskell does not know how to show functions of type P0 arrow P0. And that's because what happens in the evaluator is this thing is first parsed, then it's type checked, and then it's evaluated, and the result is displayed here. So this gets parsed, and that's okay, and it gets type checked, and it's perfectly okay. And then what happens, though? Well, it says, okay, I got to display to you lambda x arrow x. And you might think it would just display lambda x arrow x, but functions can arise in a lot of different ways. So you get the same error if I just type lambda x arrow x. So I could say, what is the type of lambda x arrow x applied to lambda x arrow x? Says, oh, that's a p arrow p. So I could apply that, I could do something here. I could say, okay, oh no, it's not. Okay, let's apply this 5. Okay, we're gonna get back 5. Let's apply to x, y, z, z, y. We get back x, y, z, z, y. So it works. We can apply it to a pair, 5 comma x, y, z, z, y. What are we going to get back? We're going to get back the pair 5 comma x, y, z, z, y. So this language that we described up here says how to define terms in the language. You can write down a variable, you can write down an application, or you can write down an abstraction. And if we can explain how these things are evaluated, then that kind of gives you the meaning. So what happens though with, let's say, suppose that f of x, y is equal to x plus y. Now, what happens when we evaluate f of 5, say? Well, what we get back is a function. It's still waiting for the y. So what we get back is a function of y, and I can write it down with the lambda term, but where all the x's have been replaced with 5. So this becomes 5 plus So how did I do that? Well, maybe it's easier to see if I say f of x is equal to lambda y arrow x plus y. So what did I do? When I evaluate f of 5, I take the body and I replace all the x's by 5, and this is what I get back. Now Haskell will complain and say, I don't know how to show you things that are functions. You know, it knows how to show us integers, it knows how to show us strings, but functions are a bit too complicated for it. It can't figure out a good way that works kind of for every kind of function that it might want to display for you. Now, that's what's happening here, is that if I have a term that looks like a lambda x arrow m, and I apply that to some term n, there's a rule called rule beta, it's called in the Lambda calculus, which says take the body and replace all the free occurrences of x in it by m. And so we'll worry about what that means in a bit. But so maybe I should say, call this the body. So take the body and replace all the x's in the body by n. Oh, let's just say that this is the actual argument. We can go over here and we replace. So take the body and replace all the x's that are in the body by the actual argument. And so that's what we just did with here. And so applying a function to, you know, one that's been defined in this way is the same as one that's been defined in this way. You just take the body and you replace the argument gets plugged in. So like here we might say lambda x arrow lambda y arrow. I forgot my lambda. X plus y applied to 5 reduces by this beta rule by saying, okay, take the body. The body is this. Well, I don't know why it doesn't. When I highlight, all right, copy, all right, paste. Take the body, that's this, and replace all the x's by 5s. And so that's just equal to, this is just the same thing as lambda y arrow, replace the x's 5 plus y. And so that's what you get there. We can do all this down inside the interpreter down in here and see the result, unless the result is a function, and then we have to, you know, we can ask the type of it, or we can apply to another argument to see the final result. You know, if I say, what's the type of lambda x arrow lambda y arrow x plus y, it says, oh, that takes a number, and then it takes another number, and it returns a number. And so if I just get rid of this colon t here, and I apply this to 5 and 6, I get 11. So a lambda expression is a way of naming, of defining a function without giving it a name. And we're going to see that this is really useful in some cases. Like map is a function that takes a function, like let's say And let's apply this to a list of 1 to 10. And so it gives you back a list. So what happens is map applies this function, which doesn't have a name, individually to each of the elements of the list. And so when 1 is the input, it says, okay, return the pair. This is a pair. Return the pair where X, which it was the argument 1, is the first element. And the second element is the string that I get by calling the Haskell function, show me this thing. And so it returns 1 and then the string of 1. And so it's just often useful to be able to do, you want to increment or double everything in the list. You can do it that way. It's just much more convenient to be able to write this. But you can also write functions that take inputs and return functions. So I can have, I don't know, funny xy is equal to lambda z arrow x plus y. All right, that's funny. What does funny do on 10 and 11? Going to be a problem. Can't show me. What happens if it says 10 and 11 and I give it left paren, right paren, which is the empty tuple, or something called unit? It's the element of the empty tuple. I could give it anything, actually. List from 1 to 10, no matter what I give it. Why is that working? Because what's happening here is a little bit weird and funny. Funny is returning a function of z, and then z does not occur in the body anywhere. But that was a little bit like what was happening here with k, because once you gave k an argument, you got a function of y that didn't refer to y. Just whatever you gave it as x got built in, and then y just returned that. So that's okay. That's just a constant function. All right, while we're talking about constant functions, let me just say one more thing here. Like, I can define a function. This is like a very weird function. This is a function that just loops forever, or whatever, recurses forever. And so I could say loop equals loop. And you might think Haskell's going to complain, but it's perfectly okay. And what's the type of loop? Loop has a type T. If T is any type, loop can have every single type. Now, what happens if I say, like, lambda x arrow 2, this is and I apply it to, okay, unit. Whoops. Need to have that backslash there. Oh, I just get back 2. What if I apply it to 1? I get back 2. What if I apply it to the empty list? I get back 2. What if no matter what but what about that loop thing? I still get back 2. Now, in programming languages that you know and love, they use strict evaluation, and Haskell uses non-strict evaluation. And strict evaluation basically says this thing here will first evaluate its argument loop. And so if loop loops forever, then this whole thing loops forever. So a strict evaluation is one where if any of the arguments loop forever, then the entire thing loops forever. But here in Haskell, we use non-strict evaluation. And so it says, okay, what does it do here to evaluate this? It says, take the body of the thing, which is 2, and replace all the x's by loop. Well, there are no x's, so it just says, oh, 2 is the answer. But if loop was evaluated first before it got substituted in, then this thing would loop forever. Okay, so you might look up strict and non-strict evaluation. And okay, thanks for listening.